Isaac Newton didn't just observe the world, he decoded the invisible rules governing every structure we inhabit today. Before his insights, the movement of the heavens and the mechanics of Earth were seen as separate realms. By realizing that the same force pulling an apple to the ground also keeps the moon in its orbit, Newton unified the universe. This leap in logic provided the foundational framework that allows us to understand how forces interact with mass, transforming physics from a collection of observations into a precise, predictive science. At the heart of this revolution is F equals ma. This deceptively simple equation, force equals mass times acceleration, is the silent guardian of our built environment. It tells us exactly how much force a structural element must withstand to remain stationary. When we look at a bridge or a skyscraper, we are seeing a calculated standoff where the forces of gravity and environmental loads are perfectly balanced by the strength of the materials. Every beam and column is sized according to Newton's second law, ensuring that acceleration remains zero and the structure stays firmly in place. Newton's genius was rooted in his obsession with change, specifically how things change over time. To describe the continuous motion of the planets or the varying stresses on a curved arch, he needed a new mathematical language. When the existing tools of his era proved insufficient, he invented calculus. This mathematics of change allowed for the calculation of instantaneous rates, giving engineers the ability to move beyond simple geometry and into the complex, dynamic analysis of loads and fluid pressures. This mathematical breakthrough is the DNA of modern engineering. Calculus allows us to model how a high-rise sways in the wind or how a foundation settles into the earth. Without the ability to integrate and differentiate, we couldn't calculate the precise distribution of weight across a suspension cable or the varying pressure of water against a dam. Newton provided the infinitesimal lens through which we view the world, allowing us to build taller, longer, and safer than ever before. Today, we often take the stability of our homes and infrastructure for granted, but every standing wall is a testament to Newton's legacy. Whether it's a small residential cottage or a massive transit tunnel, the design process begins with the principles laid down in the Principia. We aren't just using his equations, we are living inside the physical manifestation of his thoughts. The safety factors we apply and the simulations we run are all direct descendants of a 17th century quest to understand why things move and why they stay put. As we look toward a future of kinetic architecture and increasingly complex infrastructure, Newton's work remains the bedrock. While we have expanded into the realms of relativity and quantum mechanics, the classical world, the world of concrete, steel, and soil, still answers to F equals ma. We stand on the shoulders of a giant who saw the moon not just as a light in the sky, but as a falling object governed by math. And in doing so, he gave us the tools to build a world that lasts.